Okay, great. Thank you so much. And okay, great. So today I'm going to talk about EPTI for functional MRI. There's still, despite the advancement, there's still challenges in fMRI acquisition, including factors that affect the image quality, like distortion and T2 star blurring, limited ability to acquire multi-echo, multi-contrast imaging, as well as the need for higher spatial temporal resolution. So we've been developing this Echo Planar Time-resolved Imaging, or EPTI, as a new acquisition technique to address these challenges. So it's a distortion-free readout with fast sampling efficiency, provides rich multi-echo, multi-contrast imaging, and it's a versatile readout technique for various image contrast. And recently, we've been able to extend that to achieve ultra-high spatial temporal resolutions. So we've been developing the EPTI for different kind of fMRI regime, including a standard resolution to ultra-high spatial temporal resolutions. And these are designed targeting for different applications, including multi-echo fMRI, layer fMRI, as well as mesoscopic fMRI. So these different applications are we develop different kind of variants or techniques or EPTI variants that are enabled to address the different demands in these different applications. So before diving into these, I'd like to give an introduction to how EPTI works to those who might not be familiar with this technique. First, I'll start with why EPTI has distortion and blurring problems, and then talk about how to address them. So, EPI it has distortion and blurring because it's acquired different phase encoding lines at different time point, and I'm plotting the KY and T space and with different phase encoding lines, at different time point. And this shows as a diagonal line in the KYT space, and there's phase accumulation and signal decay accumulating a long time, and therefore phase encoding direction leading to the distortion and blurring. And also this lengthy readout to generate one single image also limits the number of echoes we're able to obtain after each excitation. So common approach to reduce distortion blurring, such as parallel imaging, reduces the readout length, therefore reduce the accumulated B0 or signal decay. To further reduce the distortion blurring, you can use a higher acceleration, but usually come at the cost of lower SNR due to noise amplification due to higher acceleration or shorter readout length and less thermal noise averaging and potentially more artifact. So ideally, we'd like to sample this fully sampled KYT space so we can take out the phase encoding lines that are acquired at the same time without B0 signal decay and accumulation. And also we can get a time series of distortion and T2 or T2 star blurring free images with different echo or contrast with very small T increment. But acquiring this fully sampled KYT space is it requires very long acquisition time and is impractical for fMRI applications. That's why we developed EPTI to sample this KYT space with very high undersampling factors by exploiting the spatial temporal correlation within the readout. Because this space, if you look at the space, there's a lot of data redundancy within this space, and we've designed this spatial temporal trajectory that with the neighboring data space close in time, as well as complementary sampling along the spatial KY domain, so that they have good spatial temporal correlation, so we can use the acquired data point to recover the missing data point. And the encoding can be also pretty flexible to extend from KY to other dimensions such as KZ in the form of SMS or 3D imaging. So this acquisition can be implemented in either multi-shot acquisition manner, where each shot acquire a small segment in the KYT space, which are suitable for higher resolution. Recently, we've also developed by optimizing the spatial temporal encoding to reduce the dead time or echo space into higher spatial temporal correlation to enable single shot acquisition as standard resolution with robust performance as well. So this is how we can play out this trajectory in the sequence that we can plug in the continuous readout to fill any dead time in the sequence to be very efficient, as well as plug into any contrast sequences to get multi-contrast images and potentially also parameter maps as well. So for reconstruction, we can either do a B0-informed graph reconstruction, where a compact kernel is used to kind of recover the missing data point using the acquired data. And recently, we've been able to move to the subspace approach to improve the reconstruction conditioning, which takes advantage of the signal priors and subspace spaces to improve the reconstruction conditioning to resolve the multi-echo data. After reconstruction, now we can get the fully sampled KYT space and be able to get a time series of distortion or blurring-free images with multiple TEs. So this is a quick summary. So EPTI provides us distortion-free imaging with fast sampling efficiency, rich multi-echo imaging resolved across the readout, can be used as a versatile readout technique for various image contrasts. So next, I want to talk about how it can be helpful for fMRI applications. First, I'll talk about a standard resolution regime for multi-echo fMRI. And this is where using single-shot EPTI with a single shot providing robustness to motion and physiological noise. So the goal of single-shot EPTI is to improve data quality and information content comprehensively within a comparable TR to EPI. And this is a two example protocols, two different applications comparing EPI and EPTI. You can see that the TR are comparable under the same SMS factor. It can remove the distortion and recover the signal dropout by taking advantage of the rich multi-echo information obtained within this comparable TR. So the benefit of being distortion-free, not only having good anatomical integrity, but also can improve temporal stability. Here shows the data from 3 subjects comparing EPI and EPTI. And if you look at the motion estimation, this is during like a pace breathing and interleave with the breath hold. You can see the motion parameters in EPI. You can see this apparent motion along the phase encoding direction caused by the respiration-induced field changes, as well as in the carpet plot, the corresponding signal intensity variations that are still there even after motion correction, which are significantly mitigated in the EPTI images. This is a nice illustration of understanding the dynamic distortion and the effect of delta B0 variations on EPI and EPTI images, where we do the simulation, add very strong B0 variations on the images. And this is a plot of one column images across the dynamic with different B0. You can see that this geometric changes on the EPI images leading to high standard deviation on the image that cannot be kind of mitigated well after the motion correction. And on EPTI, even with this B0 variations, even without accurately modeling the B0 update, you don't see any geometric distortion on the image, therefore leading to a lower standard deviation. There's some residual signal variation due to inaccurate reconstruction modeling that can be addressed by using a simple global B0 update already. So this shows that the time-resolving image approach determines the distortion-free nature, while accurate B0 update reduces the residual signal intensity errors or variations in EPTI. So another benefit, similar to multi-echo EPI or multi-echo fMRI, the continuous multi-echo readout can increase the TSNR efficiency. And because we can increase the readout length without introducing any distortion blurring concern, so instead of having a restricted readout length due to distortion blurring concern, we can increase the readout length to optimal readout length to enable better thermal noise averaging as well as optimize SNR efficiency. In addition to readout efficiency, the multi-echo images can be combined with the multi-echo ICA developed by Pragdi Kondo and Dr. Bettini to remove the physiological noise. And recently, our collaborators at UCSD, Katie and Dr. Tom Liu has developed MEICA Tadana denoising pipeline, for EPTI data specifically to remove the physiological noise that they will be presenting at Hawaii SMR. And these are showing the multi-echo images resolved in the single-shot EPTI images from TE of 3 millisecond to around 60 millisecond. And these early echoes can be used to recover kind of functional signals at the short T2 SAR regions. And there's also other ways to use this densely resolved multi-echo images, like our collaborators at GSU, Dr. Lisa and Vince Cajon has been using our rich multi-echo EPTI data to look at the unique TE signatures like signal frequency content or resting state connectivity to explore the rich information. And finally, I think this is another good example where we use EPTI readout in a velocity encoded sequence where you can look at both the phase and the magnitude images. And from the phase, we can get simultaneous CSF flow imaging across the subarachnoid space. You can look as well as the bold imaging. And these, you can look at the spatial temporal dynamics of these slow CSF flow in the subarachnoid space. And with this concurrent approach, enables us to study the link between CSF flow and brain activation, and we've been able to see the visual tags, the directional local CSF flow, during the visual tags. There's more details you can see at the poster at 5. So next, I want to quickly go through how we can, also look at the higher resolution to look at layer fMRI with improved specificity using multi-shot EPTI. And here again are showing how EPTI are addressing the stronger distortion at higher field strengths, as well as addressing dynamic distortion that can be more pronounced at higher field strengths. You can see the geometric changes across time that can be removed in the EPTI data. Another common issue for multi-shot acquisition is the shot-to-shot phase variations. In conventional multi-shot EPI, the shot-to-shot variation can lead to the aliasing as well as its corresponding variations along time. With our segmented approach, this instead of aliasing, we lead to local smoothing or widening of the PSF that can be, but it can be corrected after the shot-to-shot phase correction. Here's an example of how in a severe case where this kind of shot-to-shot variation lead to signal variations in the EPTI data that can be significantly mitigated after a shot-to-shot phase correction. And Dr. Zhang Shen and John Palomani has developed the variable Fleet-Bungle fleet multi-shot EPTI that further improve the temporal stability by using slice shot reordering and variable Fleet-Bungle RF call design. And looking at layer fMRI, one of the important things is to getting rid of the draining vein bias introduced by the T2 prime contamination and be able to potentially to see like more microvascular specificity, for example, in the T2 bolt. And so EPTI is able to, by resolving the echoes across the readout, you can get rid of the R2 prime contamination within the EPI, like spin EPI readout, and be able to resolve like pure spin echo with minimal T2 prime contamination, as you can see here with the better spatial specificity. And here's another example looking at the layer profile of a different echo resolve across the EPTI readout. You can see that these echoes, as you move along the spin echo, you achieve the highest specificity with minimal T2 prime contamination. And recently, our collaborator, Dr. Daniel and Laura Luis, has also looked at the EPTI data and looked at the temporal specificity by looking at long and short stimuli. And they've been seeing that the nonlinearity and the time to peak changes with the amount of T2 prime contamination, and with the pure spin echo result in the fastest time to peak as well as the highest linearity. And this removing of T2 prime contamination, I'm showing here in the the T2 bolt, but can also potentially be applied to other contrasts as well, including ASL and basal. So finally, we have a recent development based on EPTI readout to achieve ultra-high spatial temporal resolution to enable to look at the mesoscale spatial features of potentially also fast temporal dynamics. And this is done by, and this is a new technique called 3D tidy. It's from time resolve. We're developing it to time and dynamic resolve imaging with a dynamic resolve encoding to enable high spatial temporal acceleration with the 3D EPTI readout to address the distortion, as well as time and dynamic resolve substitute construction with data-driven basis extraction to achieve high spatial temporal fidelity. So there's more details today at the oral, like later, an hour later. So I'm just going to show some images of this technique. This is 500 micron ISO images with a very short volume TR, and we also push for further to 340 isotropic with a partial brain coverage with a volume TR 1.2. You can appreciate the spatial details that are present in this data. And at this resolution, we're beginning to see much detailed structures like layout generi as shown here. And on the right, we're highlighting how achieving mesoscale resolution under like 500 micron can see this detailed structure, while as lower resolution like 750 isotropic can be start to blurred out to see this layout generi. And these are showing how we are performing at the challenging brain areas where traditionally we're seeing a lot of distortions and a lot of dropout as well, and how this new technique performs. And we'll also show how using this new technique provides a good functional sensitivity in a single 4.4 minutes of run, and we have good visual task sensitivity. We'll show how increasing the spatial resolution can reduce partial volume effect even in the gradient echo contrast, as well as the capability to resolve other mesoscopic features like this V2 strength. Finally, we're going to show how, in the meantime, we can get 500 micron. We get TR, pretty short TR that can resolve respiration and get to look at good resonance network, as well as this 2 ISO protocol. We can achieve really fast TR and begin to kind of also resolving cardiac and its higher frequency harmonics, as well as good resonance networks. There's oral session an hour later on this. So with this, I hope with talk about the EPTI application in different applications are also enabled by developing these different variants of techniques and acquisition and reconstruction, just tailored to address different, different need. And we also show that, not only for fMRI, the EPTI readout base can also be used for other contrasts. We recently get to really high resolution diffusion MRI at 500 micron, 3T, as well as even higher at 70 with very good resolution. Like you can see the kind of hippocampus layers and details structures. Finally, I want to highlight we're having this EPTI dissemination for functional MRI to facilitate further technical development. We have the Siemens sequence ready already in the VE system. We're upcoming getting the to XA. We have the GE and PulseSeq upcoming. We already have a lot of interested users, and please look at this if you're interested on the sequence. And thanks for all the colleagues and collaborators, and with that, thank you for your attention. Yeah.